Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 4th, 2025, about 4 days ago. The striking idea is exploratory iteration, which trains a model to self-improve over many steps at test time by learning only single-step improvements during training, sidestepping costly fixed depth schedules, while still delivering stronger multi-step gains. The paper is titled Bootstrapping Task Spaces for Self-Improvement, and the implications for model training are quite significant. The method outperforms strong baselines across math, tool use, and machine learning engineering, induces an autocurriculum, and even raises first-pass solution quality before any self-iteration. On X, reactions highlight efficient reinforcement learning for iterative self-improvement, praise task space exploration, and note stronger performance and diversity, with 2 posts drawing solid engagement around 200 likes. Alright. The previous segment introduced group relative policy optimization and why it drops the value function. Figure 1 shows that task diversity matters because the single task curve stays flat at 0, while the +2 tasks curve climbs and stabilizes around 40% normalized score. The shaded band indicates variability, which narrows as training proceeds, suggesting more reliable learning. The takeaway is that adding related tasks unlocks learning for random acts of pizza, so broader task sampling improves learnability. So while the previous figure stressed diversity, Figure 2 shows how the policy actually creates it through exploratory iteration. The diagram presents episodes that either improve on a prior turn or deliberately diverge, which generates new starting points with learnability scores. The update step keeps only partial histories with higher variance, so the start set grows toward informative, diverse states. This loop trains only single-step iterations, yet it supports deeper self-improvement during inference. Okay, the previous figure outlined the exploration loop. Table 1 now reports outcomes across math, tool use, and MLE bench. The full method tops each domain, with math rising to about 20.4% and tool use first-turn accuracy reaching roughly 76%, which signals better initial quality and stronger self-improvement. Diverge alone comes close, especially on tool use, because explicit exploration boosts diversity. Curriculum by itself barely beats GRPO, so selection without expansion is not enough. Well, Table 1 showed headline gains. Figure 3 now traces how performance rises with more self-improvement steps. The left panel shows math accuracy climbing with improve, diverge, and exit, while the initial model stays flat, which signals successful iteration. The center panel reports higher first-turn tool use accuracy, where diverge and exit start strong and hold steady through 4 steps. The right panel tracks total return and shows a consistent edge for exit across the step budget, so exploratory diversity translates into better multi-turn outcomes. Alright, the previous figure tracked gains versus step budget. Figure 5 now shows how the training process shifts toward harder, fresher instances, and how that translates into higher MLE bench scores. The left and center panels report that improve, diverge, and exit sample from more recent iterations and at greater starting depths, which signals an emergent curriculum that pushes difficulty deeper into solutions. The right panel shows higher average at 16 for diverge and exit, so exploration that broadens starting points delivers better downstream performance. Wrapping up, 2 takeaways stand out. Exploratory iteration turns any partial solution into a fresh training task, so the model learns single-step edits that compound into deeper self-improvement at test time. And explicit diversity, through prompt divergence and distance bonuses, drives stronger gains across math, tool use, and MLE bench. Thanks for listening. I am Alex, signing off.